Hello everyone, hope you guys are doing well. My name is Wahaj Uddin. I'm a creator of Teltech 360 YouTube channel and I'm a technology professional having more than 10 years experience in different technology domains, operation, field support, mainly in data communication and in telecommunication. The purpose of this channel is to bring technology student and professional on a single page where everyone can share his or her idea or ask anything related to the technology is mainly focused on telecommunication and to set such platform onto which anyone can share or discuss technology views, technology idea and the next generation technology. Now it starts with the basic concepts of wireless communication. Here we have a chapter fundamental of wireless communication and I made a presentation for to start from the very beginning, and it is the episode 1. In episode 1 we will discuss the electromagnetic wave, electromagnetism, how it propagates, how it generates, and how we use them for our communication or in telecommunication. Now start our chapter fundamental of wireless communication, and it is the episode 1 of the series. And we are gonna discuss about electromagnetic force, electromagnetism, electromagnetic radiation. So electromagnetism is a branch of physics that deals with the electromagnetic force that occurs between electrically charged particles. The electromagnetic force is one of the four fundamental forces and exhibits electromagnetic field such as magnetic fields, electric fields, and the light. It is the basic reason electrons bound to the nucleus and responsible for the complete structure of the nucleus. The question arises, what is electromagnetic force? Basically, the electromagnetic force is a type of physical interaction that occurs between electrically charged particles, and it acts between charged particle and is the combination of all magnetic and electrical forces. The electromagnetic force can be attractive or repulsive. What is electromagnetism? Electromagnetism is a process where a magnetic field is created by introducing the current in the conductor. When a conductor is electrically charged, it generates magnetic lines of force of conductor. For example, as you can see the animation right at the right corner, if current that is positive charge moving in a wire, it produces the magnetic field along the wire, and the direction of the magnetic lines and force can be determined using right hand rule. In physics, electromagnetic radiation, or we can say EM radiation or EMR, refers to the waves or their quanta or photons of the electromagnetic field propagating through space, carrying electromagnetic radiant energy, and it includes radio waves, microwave, infrared, visible light, ultraviolet, X-rays, and gamma rays. And all of these waves form part of the electromagnetic spectrum. Electromagnetic radiation consists of electromagnetic wave which are synchronized oscillation of electric and magnetic field. In the slide you can see the picture at the right top corner, in which a linearly polarized sinusoidal electromagnetic wave propagating in the direction of z through a homogeneous isotropic medium such as can say vacuum. The electric field shown in blue arrows oscillates in the positive and negative x direction, as you can see it, at the left side, and the orthogonal magnetic field, which is shown in red arrows, oscillates in phase with the electric field but in the positive and negative y direction. In a vacuum, electromagnetic waves travel at the speed of light commonly denoted C. In homogeneous isotropic media, the oscillations of the two fields are perpendicular to each other and perpendicular to the direction of energy and wave propagation, and forming a transverse wave. The wavefront of electromagnetic wave emitted from a point source, let's say example of a light bulb, is a sphere. The position of an electromagnetic wave within the electromagnetic spectrum can be characterized by either its frequency of oscillation or its wavelength. Electromagnetic waves of different frequency are called by different names since they have different sources and effects on matter. In order of increasing frequency and decreasing wavelength, these are radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays and gamma rays. Electromagnetic waves are emitted by electrically charged particles undergoing acceleration, and these waves can subsequently interact with other charged particles, exerting force on them. EM waves carry energy, momentum, and angular momentum away from their source particle and can impart those quantities to matter with which they interact. Electromagnetic radiation is associated with those EM waves that are free to propagate themselves without continuing influence of the moving charges that produce them, because they have achieved sufficient distance from those charges. Thus, electromagnetic radiation is sometimes referred to as the far field. In this language, the near field refers to EM fields near the charges and the current that directly produce them, specifically electromagnetic induction and electrostatic induction phenomenon. In quantum mechanics, an alternate way of viewing EMR is that it consists of photons, uncharged elementary particles with zero rest mass, which are the quanta of electromagnetic field responsible for all electromagnetic interaction. Quantum electrodynamics is the theory of how EMR interacts with matter on an atomic level. Quantum mechanics, quantum effects provide additional sources of EMR, such as the transition of electrons to lower energy level in an atom and blackbody radiation. The energy of an individual photon is quantized and is greater for photons of higher frequency. This relationship is given by Planck's equation, which is E is equals to hf, and E is the energy per photon, f is the frequency of photon, and h is Planck's constant. A single gamma ray photon, for example, might carry 100,000 times the energy of single photon for visible light. The effects of EMR upon chemical compounds and biological organisms depends both upon the radiation power and its frequency. EMR of visible or lower frequencies, that is, visible light, infrared, microwave and radio wave, is called non-ionizing radiation because its photons do not individually have enough energy to ionize atoms or molecules to break chemical compounds, to break chemical bonds. Okay, now we have electromagnetic spectrum and the electromagnetic spectrum EM radiation. The designation radiation excludes static, electric and magnetic and near fields, is classified by wavelength into radio, microwave, infrared, visible, ultraviolet, X-rays and gamma rays. Electromagnetic waves can be expressed by Fourier analysis in terms of sinusoidal monochromatic waves, in which uh, in turn can each be classified into these regions of the EMR spectrum. For certain classes of EM waves, the waveform is most usefully treated as random, and then spectral analysis must be done by slightly different mathematical techniques. In such cases, the individual frequency components are represented in terms of their power content, and the phase information is not preserved. Such a representation is called the power spectral density of the random process. Random electromagnetic radiation requiring this kind of analysis is, for example, encountered in the interior of stars and in certain other very wideband forms of radiation, such as the zero-point wave field of the electromagnetic vacuum. The behavior of EM radiation and its interaction with matter depends on its frequency and changes qualitatively as the frequency changes. Lower frequencies have longer wavelengths and higher frequencies have shorter wavelengths and are associated with photons of higher energy. There is no fundamental limit known to these wavelengths or energies at either end of the spectrum, although photons with energy near the Planck's energy or exceeding it, far too high to have ever been observed, will require new physical theories to describe. Radio and microwave. Basically, radio waves have the least amount of energy and the lowest frequency. When radio waves impinge upon a conductor, they couple to the conductor, travel along it, and induced an electric current on the conductor surface by moving the electrons of the conducting material in correlated bunches of charge. Such effects can cover macroscopic distances in conductors, such as radio antennas, since the wavelength of radio waves is long. Electromagnetic radiation phenomena with wavelengths ranging from as long as 1 meter to as short as 1 millimeter are called microwave, with frequencies between 300 MHz (0.3 GHz) and 300 GHz. At radio and microwave frequencies, EMR interacts with matter largely as a bulk collection of charges which are spread out over large numbers of affected atoms. In electrical conductors, such induced bulk movement of charges, electric currents, results in absorption of the EMR or else separations of charges that cause generation of new EMR, effective reflection of the EMR. An example is absorption or emission of radio waves by antennas or absorption of microwaves by water or other molecules with an electric dipole moment. As for example, inside a microwave oven, these interactions produce either electric currents or heat or both. Infrared. Like radio and microwave, infrared also is reflected by metals and also most EMR, electromagnetic radiation, well into the ultraviolet range. However, unlike lower frequency radio and microwave radiation, infrared EMR commonly interacts with dipoles present in single molecules, which change as atoms vibrate at the end of a single chemical bond. It is consequently absorbed by a wide range of substances, causing them to increase in temperature as the vibration dissipate as heat. The same process run in reverse causes bulk substances to radiate in the infrared spontaneously. Infrared radiation is divided into spectral subregions. While different subdivision schemes exist, the spectrum is commonly divided as near infrared 0.75 to 1.4 micrometer, short wavelength infrared 1.4 to up to 3 micrometer. Mid wavelength infrared is 3 to 8 micrometer. Long wavelength infrared is 8 to 15 micrometer and far infrared 15 to 1000 micrometer. Visible light. Natural sources produce EM radiation across the spectrum. EM radiation with a wavelength between approximately 400 nanometer and 700 nanometer is directly detected by the human eye and perceived as visible light. Other wavelengths, especially nearby infrared longer than 700 nanometer and ultraviolet shorter than 400 nanometer, are also sometimes referred to as light. As frequency increases into the visible range, photons have enough energy to change the bond structure of some individual molecules. It is not a coincidence that this happens in the visible range, as the mechanism of vision involves the change in bonding of a single molecule. Retinal, which the rhodopsin protein it is contained in, which starts the biochemical process that causes the retina of the human eye to sense the light. Well, in Animal that detects infrared make use of small packets of water that change temperature in an essentially thermal process that involves many photons. Infrared, microwave, and radio waves are known to damage molecules and biological tissues only by bulk heating, not excitation from single photons of the radiation. Ultraviolet. As frequency increases into the ultraviolet, photons now carry enough energy, about 3 electron volts or more, to excite certain doubly bonded molecules into permanent chemical rearrangement. In DNA, this causes lasting damage. DNA is also indirectly damaged by reactive oxygen species produced by ultraviolet A UVA, which has energy too low to damage DNA directly. This is why ultraviolet at all wavelengths can damage DNA and is capable of causing cancer and for UVB skin burn, sunburn that are far worse than would be produced by simple heating temperature increase effects. This property of causing molecular damage that is out of proportion to heating effects is characterized of all EMR with frequencies at the visible light range and above. These properties of high frequency EMR are due to quantum effects that permanently damage materials and tissues at the molecular level. X-rays and gamma rays. Electromagnetic radiation composed of photons that carry minimum ionization energy or more, which includes the entire spectrum with shorter wavelengths, is therefore termed ionizing radiation. Many other kinds of ionizing radiation are made of non-EM particles. Electromagnetic type ionizing radiation extends from the extreme ultraviolet to all higher frequencies and shorter wavelengths, which means that all X-rays and gamma rays qualify. These are capable of the most severe types of molecular damage which can happen in biology to any type of biomolecule, including mutation and cancer, and often at great depths below the skin. Since the higher end of the X-ray spectrum and all of the gamma ray spectrum penetrate matter. Here is a chart for different classes, their wavelengths, frequencies, and energy per photon. It is for your review, and this was the end of the episode 1. That was the very basic and fundamental concept of wireless communication, and it is still we will discuss it in further presentation in the upcoming presentations, which will be discussed in episode 2, and it will be about radio waves, wireless signals, and frequency. So please keep watching, like, share, comments, subscribes, and especially comments and discuss about the topic, discuss about the wireless communication, discuss about telecommunication. This is what this channel has made for. And thank you for watching.